Does everyone have to acknowledge the recording?
I'm not sure on.
Because it sent me a thing that said recording is in progress, and then it had a continue button, and I assume that means that each person has to opt in on the recording.
Probably have to do that, yeah.
Yeah, I think if you hit the other button other than OK, that Zoom will automatically end your session, and you will be forced into leaving the particular meeting.
Well, that's nice.
I'm glad I
Okay,
didn't hit that button.
okay, so we're now recording. Welcome to the June Seattle Robotics Society meeting. And yep, we're actually on with Zoom. So please mute your microphone. Please note you're being recorded. Sounds like everybody's had to, at this point, if you're still here, you had to hit the accept button. If you open up the chat window, I've placed a link in there to a notes document. So if anybody wants to drop anything in the notes for the meeting, you all should be able to edit that document. Let's see, we're going to follow the typical agenda here, and let's go from there. Yep, there's the shared document. That link is, yep. Okay, so it's actually in the chat window. It's a Google shared document. First off, first law is going to be at a new location in the fall, somewhere between Kent and Tacoma. We don't know yet. Probably could have asked Kevin about that while he was here, but he may not know yet either. One other question for folks. Feel free to raise hand or unmute. Steve is looking at a speaker from Japan. Are people open to a late meeting, or like later in the afternoon or later in the evening, so we can get a speaker from Japan in? What's people's folks on that, or what's people's thoughts on that? Okay, Colin sounds good. Anybody object? Michael's good. Mitchell's good. Robert. Okay, so we'll call that okay. Okay. We're probably going to continue doing the online meetings, even once we go back to in person. So we, as of yesterday, picked up a Zoom account. So that this meeting link will be the meeting, basically the meeting link for going forward. We won't be using Microsoft Teams anymore. We are going to need people to help with the meetings once we go back to in-person meetings. So we'll need one or two people to kind of run the AV gear. So just let Steve or myself know at the SRS email below. And
Lloyd, could we go back to that one last previous screen there? So
yep.
How will that work as far as, I'm assuming that we're talking about right now a hybrid approach?
Yeah.
Meetings. Okay, so can you articulate a little bit about what is that going to look like?
So to be completely honest, we don't know yet. The way I've done this in the past is, and this will somewhat, well, it'll largely depend on the venue that we end up getting into. There'll be a computer and camera in the room, and that'll at least record the session and provide the out feed. If we get lucky and get into a room that's set up for this, so like for C++ users group, we were actually planning to use the Microsoft Reactor rooms, which we could use if we have a Microsoft sponsor. They actually have their full teleconferencing setup. So there are multiple cameras in the room to record the speaker, record the audience. There's microphones in the ceiling, so the audio is great. And there's a monitor in the front of the room that shows the remote camera feeds as well. So if we get lucky, that would be the ultimate setup. If we don't get lucky, we'll kind of make it up as we go. Probably something on that model. There'll be, one webcam type camera in the room to record the speaker, And probably a monitor up front so people can see what's happening on the web feed. So
Okay.
we'll have to play with it as we go.
Mhm.
If anybody has any ideas, that'd be great too.
And then also as far as contest events or, like these virtual events that we've been doing and what's coming in the future virtual wise for contests, we might want to, in addition to our in-person Robothon event, we might want to consider hybrids that way as well.
Oh yeah.
In other words, where, occasionally we have totally virtual contest or events in addition to the live once a year event. So
Yeah, totally agree. I am a total fan of this the hybrid model. So some of you know I work with the CPP Con, which is a full-on international conference. It went to a hybrid model. Well, it's going to a hybrid model this year. Last year it was full remote, and basically within like an hour or two of last year's conference, it became glaringly obvious that the hybrid model is the way to go. We had people that were able to join that, like I've never been able to come to the conference before because I couldn't travel, I couldn't afford to, have whatever reason. But it was very clear there was a much bigger body, let me phrase it this way, a very large body that was not being served because it was only an in-person conference.
Yep.
So it was, it's hybrid's the way to go.
Yep. I agree.
We'll be doing that. I don't know exactly how that's going to play out yet, but and I'm sure it'll evolve over time as we figure out, hey, here's what we're doing, here's what we need to do.
Sounds good. Thanks for touching on that.
Yep. Okay, let's see. SRS community outreach, kids robotics classes. Steve is doing a weekly robotics class, teaching about 4 to 6 kids at a church in Burien. I'll let Steve talk a little bit more about that when he's back. He's mentioned it before, but I am not super familiar with exactly what he's doing other than what's on the slide. Okay, the SRS website's getting a major upgrade. We're going to add an improved getting started section. The video that we're recording now will be on there. Basically, if you have thoughts or comments, let us know, and actually let Steve know. And there'll be some moderately technical stuff as well. So that's in process and coming down the pipe. So today we have Joseph Norby. He's going to talk about Cheetah Tails and how they can help robots move. We'll probably be getting that started about 11 o'clock. So we'll do our normal thing of around the room and have a little break, and then we'll get going with Joseph. And again, big thank you to Kevin for jumping in and rescuing me here so we can actually share slides and screens and record things today. Let's see. The coming presentations are posted on the SRS homepage. Oh, there's the question from Steve. How many folks would attend a one-time late afternoon meeting? We've already handled that one. I didn't realize you had that in there. Okay. I believe Steve, let's see. Steve's always looking for presenters. Just email him at srs@gmail.com and he can get you going. Let's see. So he does have most of this year booked up. So let's see. Yep, he scheduled everything for online. And there's the layout for the rest of the year. Let's see. Oh, those are all looking pretty good. Cool. Oh, one thing to note, the August meeting will be a little bit special. So it's going to start about 10:30, and that will be a coverage of the DPRG, which is the Dallas Robotics Group, Dallas, Texas. They're going to do a Robo Columbus event, which is very similar to our Robo Magellan. Also, he does not have it on here in July. Oh, we got another slide on that. I'll talk about that when we get there. There we go. Next event is going to be on July 10th at noon for us. So this will be a virtual Robothon event. It'll be a Robothon exhibition. We currently have 8 speakers lined up for this one. So it's going to be about it's going to be 2.5 to 3 hour event starting at noon. And yeah, it'll be basically videos and people talking about their projects. It'll be very much like our Around the Room that we do beginning of every session, but more in depth. I will also note we've got, in addition to those 8 that are signed up, we've got at least 2 or 3 more. And Donna, you may have gotten some more since then. I don't know. So we are going to schedule another one of these. I think we're talking about October. Yeah. So it'll be late September, early October. So we'll have another one of these virtual Robothon exhibitions. And even when we go back to the full-time or the in-person Robothon event, which will be sometime in 2022, by the way, what we're talking about right now, we will continue doing these exhibitions. The turnout for this, at least for speakers or presenters, was really, really impressive. So we got like 10-ish people right off the bat. So we're going to try and continue this going forward as well. There's the Robo Columbus, Dallas Personal Robotics Club, August 21st. They'll start at 10:30. Tune in during our meeting. So no SRS meeting that month, but we'll all join into the DPRG event. Okay. Basically, we've still got some open discussion forums running around. Looks like Steve's got the events for this year pretty well filled out, but if there's any other ideas for open topic discussions, let Steve know. We use those to fill in when we don't have speakers. If you're interested in purchasing a workshop robot kit, we still have both the Arduino and the propeller-based kits available. So the Arduino Uno is $125. Yep, I've got some here. Steve also has some. Just drop us a note and we'll figure out how to get it to you. We take cash, check, credit card.
Do you have the multi-core versions too?
Yep. So there's the propeller chip version, and it's 135. So we've got those as well.
Great.
Let's see. Okay, yep. So the virtual robot discussions, workshops. At the end of this meeting, we'll actually stop recording. And I believe if people want to continue to hang out, I believe Zoom will let us just stay, keep the meeting open for as long as we want. So it should not be a problem. Works the same way as Teams. You won't be recorded, but people can hang out and talk, and work on your projects for all afternoon or into tomorrow if you feel like it. Okay, so around the room. This is a little interesting the way Zoom presents this to me. So if somebody wants to present, let's do this. I'm not sure I can see everybody's hand raised because of the way this is presented. Hang on just a second. That's better. There we go. Okay, now I can see everybody. Okay, who has something they would like to present? Nobody? Come on, guys. We're either going to have a really long break or we're going to start the main session early. What do you want? What do you guys want to do? Oh, wait, Fred's showing something there. Oh, Fred, you look like you got something to show. Maybe.
Yeah, I can show you some. This is my Rover. As you can see, it's a little goofy. So yeah, that's the magic box, basically a Pixhawk, nothing special. Upboard right there. That's the brains, runs Ross, all that fun shit. Pixhawk, of course. A little connector I built because you don't want to cross, neither do you want to cross streams, nor do you want to cross voltages. So that guy is probably way more complex than it needs to be. One of the nice things I built into this thing, and I haven't got the whole thing 3D printed, but this is essentially can flip down. You can also see, and I'm doing this without looking, so I don't know. Oh, there we go. I've got the right thing. So you can see where I basically, this is NGen is the plastic, and I built essentially a plug board back here. And so this guy actually connects directly to the upboard's output, HDMI output. This guy right here is the USB to my Pixhawk, goes straight through here. So basically I made it easy to remove. This whole thing pulls off. It's actually pinned on here, so I could literally remove it. So that's been my fun. And it's just your basic RG Rover. So it's nothing really all that special. Except for the fact that we did okay on a Robomechanics in a vehicle much like this. We used an Xmax in that case. And frankly, those things are nice. It was $800, I think, when we bought it, and now they retail for $1,000. They're fifth scales, and they can only do maybe 50, 60 miles an hour. So, you know, nothing lightning fast. You're not going to win a drag race for it, but if you put the right end effectors in the front, you'll mow down all the little kids that get in the way, you know, Robomechanics. I mean, no, you would never do that. This isn't on film, right? So anyway,
I think you lose points on the safety rules for that.
That's actually, it's surprising that we had a couple of these guys, and just your straightforward plain Jane sonar Ardu pilot was able to deal with all the kids going up there and baiting the robots. Hey, little robot. Seriously, they were crazy. And it was funny to see how well the robot performed in a crowd. There was nobody doing anything special at Robo games to manage traffic. And yet it just worked fine. So anyway, that's kind of what I'm doing. I don't want to keep rattling on about this. I haven't touched this thing and yet there I go. I haven't touched this thing for a year and a half here. And over at Robot Garden, we're running an outdoor Rover build fest. So a bunch of people are getting Pixhawk and Pixhawk variants and building, and apparently they've collected a number of rovers, RC rovers at Robot Garden. This is in Livermore, California. And so they're building rovers, and I'm kind of leading the herd here. And we're going to be trampled by it. We don't know, especially when we get the Xmax. So that's what we're doing. We have our strictly rover style rovers and drones meeting on Tuesdays, every other Tuesday, one coming up here on Tuesday. And then today at 2, we've got just the robot hour, which is come in, show us your robot, talk about robotics, that kind of thing. More of a show and tell and questions and answers session than a specific build. But again, Tuesday, we're hammer and tongs on building RG pilot style rovers. So if you're interested, certainly come on. We're on a meetup as Robot Garden. And hey, guys, really love the virtual meetings. I'm way the heck out of town. I'm 3 hours away from 3.5 hours away from Robot Garden. There's no way I can get to there. And yet I've gone to meetings, I've gone to seminars and that sort of thing during the COVID. So this has been really good. Love the virtual. Keep it up. Thanks so much for your time, guys.
Yeah, hey, quick question. Could you tell me a little bit more about this Pixhawk processor that you're using?
The Pixhawk? So the Pixhawk, I'll show you this. I'm not sure that that's going to be as informative. The one that a bunch of us are loving. I've got stuff caught in my camera. There we go. This is the Pixhawk. I don't know if you can see it because the problem is it's got that bright green light. Let me turn off the light. There we go. And that's what a Pixhawk looks like. So it is an ARM processor that's got a backup on it. And this is a Pixhawk.
Oh, that's interesting.
Go ahead.
That's interesting.
Yeah, it's basically, they are navigational computers, global navigational computers that rely on the GNSS systems, of which GPS is one. So there's GPS, there's Baidu, there's GLONASS. I don't remember what Japanese is. Galileo is European. I think that's all there is now, 5. And so this thing actually uses GNSS. If you're familiar with Mission Planner or APM Planner 2, those guys allow you to actually, so the ArduPilot software is designed originally for copters, but it's now used in rovers and boats and planes, and I said copters and subs. I'm not sure how that works in a submarine because you sure can't get GPS underwater. But in any case, probably a dive, and mapping.
You probably dive and pick up. It's probably a Coleman filter that picks up when it surfaces, and then it's just inertial under the surface.
Exactly. That's what I figured, but I haven't built one, so it's speculation. But yeah, go ahead. I'm sorry.
That was just my guess.
Sure. So does that make sense in terms of ArduPilot is the navigation component? So its primary sensor is a GNSS, right? It also has compass, also has inertial, that kind of thing. Let's see, what is that? A gyroscope, inertial, and something else. I can't think what the third one is. You guys, the typical 3 in an IMU, right?
Yeah.
Plus, it's got compass, so you know your heading, and so which is kind of nice to know which direction the thing is pointed.
Yep.
What we did in terms of, since I'm surprised this is, where your interests lie. It's one of those things where if I know it, everybody must. So so how we did this is actually kind of cool. You communicate to the rovers using a link called MavLink, using a protocol called Mav, I believe, or MavLink protocol, one of the two. In any case, that's a serial protocol in my case, I'm using 915 megahertz radios, use a different frequency in Europe. But basically, I connect using the ground control station to the rover. Using that, I can plan a mission. So a mission can be some arbitrary space, and I can say, go fly a mission or drive a mission for that matter, that's going to, kind of raster the whole thing. So in other words, it'll go through the whole darn mission. It'll plan it itself. And that's kind of a pre-plan out of there. The way we actually used it was we had waypoints and a certain, because, elevation is semi-meaningless for a rover, semi. In any case, what we used is we used the elevation to trigger the rover to change states. So when we started it off, it flipped into auto mode, which basically means fly or drive by waypoints. When it came to a certain waypoint, we knew what orientation was because it was driving that way. And that waypoint says switch modes. Specifically in our modes, in our case, since it was Robomagellan, we switched into cone finding mode. So that's what we did. It was in cone finding mode, hits the cone, switches mode into backup mode, which is basically back up and to the side. And I know presentation, I think, was it here or was it Dallas that we saw somebody talking about a non-GNSS rover that used various different mechanisms to get out of trouble. It was really pretty cool. But yeah, ours is very simple, right? We're dealing mainly with turf and blacktop and no big bumps, picnic tables, which took out a number of bots, but no big bumps. So that's kind of how this thing drove. It was very simple. I mean, from concept, it's really, we're either driving by mission, we're finding a cone, or getting the heck out of it, or stopping because we're already at the finish. So it's really, really simplistic. I can imagine people could go crazy with this. But again, we had ROS nodes that were reading this information, using an ML algorithm to actually find a cone and then drive closer to it. We have videos of cones that are being found. It draws, for the user, we drew green rectangles around these cones. So camera flashes on the backyard, and all of these green rectangles pop out where the guy had a dozen cones in his backyard.
Oh, that's
So he was
cool.
having fun with it. It's pretty cute little video. I'll paste it later.
Yeah.
And we've got Ghost Cone, which is actually really a cool one. Basically, different guy, the guy who was actually building the equipment, took a tiny cone on the end of a fish line. And so you see this cone kind of float into view, and the wheels start turning. And as the cone moves left and right, the wheels are following. So it's actually, it's a POC. Does it work? Does it follow a cone?
Right.
And yeah, that was kind of cool too. So I'll post that one too, because that's just,
Yeah, those would be
it's
fun.
fun.
I'm actually thinking that would be fun to have one of those guys give a presentation to this group too.
Sure,
That would be-
sure.
If they're interested, feel free to have them get in touch with Steve, because that would be super interesting.
Yeah, we've got Marco, who's like, just makes us all look stupid. And he does. It's just terrible. He is so good at this stuff. His builds are astounding, and he's great at software. He's pretty darn good at electronics too. But yeah, I will mention that to him. He may be interested.
Yeah, that'd be cool. Okay, thank you.
Other questions?
If anybody's got questions, just go ahead and open your mic and go for it.
What's a good resource site for Pixhawk? I posted some things, but I wasn't sure if they're really the best references. I found Pixhawk.org and docs on Pixhawk 4.
Yeah, so the Pixhawk.org is going to be talking about, current build and that kind of stuff. This thing is a whole system. So I would say probably starting on arduPilot.org is a great place to start. Why? Because they break down their build into effectively the 5 that we talked about, right? The rovers, the copters, the planes, the ships, and the subs. So literally left-hand nav, you can click on one and find it. Secondly, they do actually cover a very, encapsulated version of the electronics. So for example, I had to put these sonar units on, these guys right here, you can barely see. So those guys, it covered what to do electrically, how it works internally, that kind of stuff. So arduPilot.org is fairly complete. It is not the only solution out there. So the Pixhawk will run the arduPilot software, as well as, I can't think of the other manufacturer. They recently changed the OS, used to be NutX. Now I can't remember what it is. Again, it's an ARM processor, so the thing is rocking. It has a backup processor in case the first one fails. This is because its original use was drones. And so it's actually, so the biggest negative for the Pixhawk is the connectors are exceptionally delicate, as in they're rated for 20 insertions lifetime. So they are surfing. Yeah, exactly.
Really?
Don't screw that one up.
Yeah.
They are. Sorry, go ahead.
That sounds as bad as aerospace stuff. Oh, it sounds.
Oh,
bad.
aerospace. Yes.
Where you have to, like, every time you connect the thing, you have to count it and record it.
It's that bad. It really is.
Wow.
So the connectors on here are Molex. I can't remember what they are, but I can find it if people care. And it took a while to figure out what the hell they were. They are Molex connectors. You can get the, what are those guys in Minnesota? I should remember. DigiKey. DigiKey sells really cheaply tons and tons of the different size connectors, just pre-built. Wires already in them. You don't have, because building that connector would be a problem, right? So having said that, there are a ton of other manufacturers, and the one that we're looking at right now, I believe, is called Maytech. And a lot of us really are thinking it's normal connectors, right? So in other words, was it DuPont connectors? So that's your classic 0.1 inch distance and color coded and way easy. And I believe what was the name of let me go and look at the Rovers channel here and get you the name of the Maytech. Maytech. Oh, here we go. This is, again, I'm just using my old device, but I'm thinking about getting this new one because frankly, it's really nice. So yes, warning, Pixhawk connectors rated for only 20 inserts and removals. Yes, yes, it is. So yeah, that's this is a little bit nicer device, this Maytech, and Maytech makes a number of different models, and this is but one of them. One of the other things that we've done is how did I get there? Somehow I'm in this Ubuntu thing. There we go. Man, things are going nuts. I'm just quitting on that one. Oh, I'm locked up. I don't know what's going on, guys. Oh, I'm back. There we go. Okay. So yeah, the Maytech. Oh, did I get that in chat? Did it work? Yes, it did. So the Maytech, really nice. That one particular, really good. And the other thing that we've done is we've gone to centimeter level accuracy, which is provided by real-time kinematics, or RTK, and using L1, L2 GNSS, or GPS, if you will, GNSS really, antennas. So that gives you centimeter level, in other words, half-inch,
Cool.
typically up to half-inch level accuracy. So from following the same path, if you're doing a farm bot, or solving a hunt or something like that, then yeah, half-inch accuracy, very helpful. So yeah, that's what we built into these things, and it's pretty much stock parts off the shelf.
Oh, that's cool. Thank you. Yeah, very interesting.
Very neat.
Okay, does anyone else have something they'd like to share? Okay, well, I'll tell you what, let's go ahead and go for a 10-minute-ish break, maybe a little longer, and then we'll come back and get going with our main presentation. I'm going to see if I can get a timer up here. And we'll figure out how to pause the video. Okay, are folks about back? Give people a couple minutes to filter back in here. See,
I'm back. I represent.
Cool, awesome. And better yet, I can hear people, so the audio is still working. Okay, so at this point, I'd like to turn the meeting over to Joseph Norby from Carnegie Mellon University. He's going to talk about Cheetah Tails and how they can help robots move better. So I'm going to stop sharing, Joe, and take it away.
Awesome. Give me a minute to set up my screen share. There's some construction in the building next to me, so hopefully Zoom can filter that out all right.
Yeah, so far I haven't heard anything, so I think we're in pretty good shape.
My cat also found a fly that's apparently in the house, so if you hear some crashing in the background, that's her fault. Okay,
Got one of those as well. They work great for debugging.
Oh yeah, I have a whole folder of cat videos that I use as inspiration for research stuff. So they're much better at moving than all of our robots by far. Can everyone see these slides okay?
Yep, slides look good.
Great. Yeah, thank you so much for inviting me to talk today. I've actually never been to Seattle, and I wouldn't be able to without being virtual, although my twin sister is doing a PhD program in biophysics out there. So I'll visit at some point. But yeah, so today I'm going to talk a little bit about some of the work I've been doing at my research lab at Carnegie Mellon. I'm in the Robomechanics lab under Professor Aaron Johnson. Mostly I'm going to talk about this project that I did recently on designing tails for legged robots that were sort of inspired by cheetahs. And I'll talk through sort of the inspiration and the design process, some of the tests we ran. And then at the end, I'll touch on some other projects that we're doing. I think I can see some of you, so if people have questions, feel free to interrupt or raise your hand if you want. But if I don't get to you, just interrupt. And if someone posts something in the chat, let me know. Happy to answer questions as we go or at the So I mentioned that our lab is called the Robomechanics lab. And sort of the underlying goal amongst all the projects that we do are trying to get robots to be able to go anywhere in the world. Most industrial applications, as I'm sure people here are aware, especially for mobile robots, are generally in pretty controlled environments, whether it's sort of a factory floor that you can design so that your robot can sort of locomote around it as you'd expect. Roombas in homes that can sort of map out roughly where the obstacles are, but they can kind of assume relatively flat ground. Self-driving cars are starting to become more popular, and that's environment is certainly less structured than a factory floor. But they can still make sort of assumptions about that there are roads that are where they want to go. And even they struggle if there's a block on the road. Our lab is focusing on sort of what the missing puzzle pieces are to take robots outside of those constraints and put them sort of off-road anywhere we want to go, whether that's on Mars, different sort of rough and remote areas of the world, disaster scenarios, even places where humans might move around, but the structure or the dynamic obstacles of the environment make it difficult to move. We're focused on how we can get robots to be more successful in those areas. And so the approach that we use to do this is sort of very holistic. We don't just design robots, we don't just control robots, we sort of look at all aspects of the problem. And the name Robomechanics sort of stems from biomechanics, which is the field of studying biological systems, and the mechanics involved there. We sort of apply the same concepts to studying how robots move and how we can either change how the platforms are designed, how we implement the sensors, what controllers we use, and how all of these things come together to produce sort of interesting behaviors to be able to move more successfully throughout the world. So most of what I'll be talking today would probably fall under platform design, but we certainly have other things that, and especially that I've been working on in some of these other areas. So I mentioned that we want robots to be able to work in more unstructured environments. And so as a result, we tend to focus quite a bit on legged robots, as those systems are pretty well suited to those environments. So here's a video. Hopefully the videos play relatively smoothly. If they're choppy, not sure there's much I can do about it, but hopefully you get the gist of things. Here's one of our quadrupedal robots in the lab. It's a robot called the Minotaur from Ghost Robotics. And it's trying to get over this log here. And it's able to step over it, which is probably already better than some wheeled systems would do, but it's stuck. However, because it has legs and it can sort of interact with the world in a number of ways, we can use it to jump over the log. And so it's not just the fact that it can, that was supposed to loop, let me do it again. It's not just the fact that it can necessarily step, which is good for getting over obstacles, but we can choose where our robot interacts with the world and how. And those sort of choices make legs very desirable for dealing with structures that you may or may not have encountered before. The downside to using legs is that you are very reliant on the contact with the ground and how good of a control you have, because balance is now a thing you need to care about with wheeled robots. Balance is, in most cases, largely trivial. Certainly not if you try to drive up these. But here's a newer robot in the lab. This is one I'm using more now. It's the Spirit robot from Ghost Robotics. And you can see that it's unaware that there is this rock in front of it. Shoot, that was supposed to do. Unaware that there's a rock in front of it and tries to step up it, but because its expectations about where the feet should go fail, it falls over. And it doesn't really have a good way to correct for this, because its legs are sort of flailing, they're slipping, sometimes they're not in contact with the ground. And we'd like to be able to prevent the robot from falling, even if the legs are sort of not doing what we want. And so we can take inspiration from biology for this, and in particular, systems with tails. So here is a side view of an agama lizard. These lizards have tails that are a little bit longer than their body and are relatively heavy. And here it's trying to, can you see my cursor? I guess we probably can, but I think, yeah, there's a laser pointer. It's got some treats up here that it's trying to get to, and there is a block with some sandpaper on the top. And so for the video, you'll see it's going to run, jump off the block and make it to the treats. And because there's sandpaper there, it's relatively stable and it does this just fine. But when they replace that sandpaper with this slippery surface, you can watch the foot slip. However, as it does, its tail pitches wildly to prevent the robot from sort of smacking face first into the block. Down here, you can see sort of a trace of the tail angle, and it's able to regulate this body angle in blue, even though there's no feet on the ground. If you could flail the legs and they do a little bit, but when you're in the air and you can't rely on contact, there's sort of nothing else you can do except for something like this, where you can use your tail. So a lot of roboticists have been inspired by this, and tried adding tails to the robots based on often certain animals that they're sort of referencing. The first sort of classic example of this is the MIT Leg Lab had a kangaroo-inspired robot called the Uniroo, which is a one-legged hopper that had this big tail in the back that it would use basically just to maintain the balance of the leg while it was jumping around, especially when it only has one leg. It would be really very hard to use sort of the contact forces at that leg to both drive the robot forward and stabilize. So by offloading the balance control to the tail, it can pop pretty nicely and stably. But besides just sort of balancing in regular locomotion, it's also been used, and this particular one over here was inspired by the agama lizard, to stabilize after falls. So here's one. I'm going to move the text box here so I can see it. There we go. Here we have a robot that's about to fall off of a cliff. Generally not recommended, but this robot luckily is equipped with a tail, which it can swing in one direction. The idea here being that via Newton's third law, if you apply some torque to that tail, it applies the opposite reaction to the body. And so instead of sort of face planting to the ground, it can land on its legs and continue walking forwards. People have even used tails not just for sort of balance and rejection of disturbances, but also for driving locomotion itself. So this one down here was inspired by the Jerboa. This is a smaller robot that has a tail and two legs, which have parallel springs. Oh, that was not looking at it. Two legs that have parallel springs, but no actual actuation of the extension of the leg. All of the force required to move the system is injected via the tail sort of pumping up and down, and it bounces along on those springs. So there's been a number of different things that people have used tails for in sort of clever ways. If you notice though, all of those tails sort of look the same. They're all basically a big mass on the end of a stick. The reason for that is via Newton's third law, you apply some torque on the tail and you get an opposite reaction in the body. The lighter the tail is, generally, the faster it swings, and at some point it smacks into your body. So if you can make the tail have a lot of inertia, so by having a large mass far away from the axis of rotation, then you're pushing against more inertia and your body will move more for how much the tail moves. So that's sort of, and I'll talk a little bit more about how that works. That's sort of the effectiveness of the tail. But the downside is there's a lot of reasons that you might not want a big mass on the end of a stick attached to your robot. For one, it just adds more payload, and especially for legged robots, where you sort of have to actively lift your body off the ground as opposed to wheeled robots, which can sort of just let the passive structure support the load. Adding additional payload is generally not what you want. In addition, besides just sort of having these more practical issues, you also run into this issue of momentum transfer. So you have to swing the tail in one direction to try to stabilize your body. But now you've dumped a bunch of momentum into that tail that has to stop at some point. Most of these tails can't continue rotating forever. So either you have to apply counter torque to slow it down, or it smacks into your robot and you get a big impulse and it sort of does the same thing. And that's, so you get this like brief little window of control, but then it's kind of all undone a little bit later. And lastly, oftentimes, I mean, it's a mass at the end of a stick. So if you want to support that, unless you're just going to sort of leave it up and actively stabilize it the whole time, it gives you this weird moment due to gravity, which is generally not good for trying to walk smoothly. If you watch the video of it walking off the cliff, the whole gate is kind of bouncy as it's trying to figure out what to do with this big mass at the end of it. One other issue is that you don't get to do any external work on the system. And so if you're in the air and angular momentum is conserved, you can apply a torque to the tail and it'll apply it to the body. But once you stop, once the tail stops moving, then the body stops moving too. So you're sort of constrained in how much you can actually move the system. It's also hazardous. If you've ever worked with a big mass at the end of a stick on the end of a powerful motor, it's kind of terrifying, especially if you have a bug in your control clip. So generally we try to avoid attaching clubs to our robots. And so if we can get away from this, that would be great. And so we can take further inspiration from biology because we noticed that most animals, a lot of animals have tails, and most of them don't look like big masses at the ends of sticks. A lot of them have tails that are lighter and covered in fur. So on the left here is an example of some gibbons chasing each other, and one of them is going to jump. There we go, jump off of this tree, and you can see its big fluffy tail sort of whipping around in the air behind it as it's falling. Here's a great example of where legs aren't going to help you when you're falling like, I don't know, 20 feet. But it's able to use that tail and whip around behind it to sort of correct and self-right in the air so it can land safely. So that's an example of a sort of aerial reorientation, but terrestrial animals also seem to use this. So one of our collaborators, Amir Patel, has done a bunch of research on actually studying cheetahs and then trying to make robots based off of them. He got a bunch of footage from some cheetahs in a wildlife sanctuary chasing things and studying their tail, and you can see that their tail is going crazy as they're accelerating, decelerating, turning. They seem to really be whipping it around. And for a while, it was thought that, oh, this is just sort of a counterweight or a rudder, kind of like these inertial tails. But then Amir was invited along on an autopsy, and it turns out that a cheetah tail is only about 2% of the mass of the whole cheetah, and most of that is muscle at the base of the tail. So its inertia isn't that high. So then the question is then, how does it use that tail to actuate the system? And we think that aerodynamics has a play in there due to the fur on the end of the tail. So then the question that was posed to us is, if we think that aerodynamic drag might be useful for a tail in sort of stabilizing your body, to what extent is it actually effective? Can we actually get enough sort of torque out of just drag, which is something that you usually neglect in most robot models, to have a noticeable or even beneficial impact on the locomotion of the system? So this is sort of the question that we were trying to answer, motivated by those insights. And so in order to go about answering that question, we went through a couple different steps. And first, we wanted to create a model so that we can actually look at some of the math and try to quantify how effective aerodynamics could be, and also see if we can use that to extract some insights. From those insights, then can we design a tail to try to maximize how effective the tail can be. And not necessarily just by mimicking a cheetah tail or a gibbon tail or whatever, but by sort of looking at the model, we're leaving the realm of biomimicry and entering bioinspiration, similar to how wheels might be better in some cases than legs. We want to build the best possible tail that we can from that model. And then we want to test that out, because without showing that on a hardware platform, it's hard to know if it's actually going to be useful. So here's a little preview of what I'll be talking about. And so we're not the first ones to look into the effectiveness of tails, although not that many people have looked into drag. There won't be too much math in this talk, but the next like 2 slides have some math. It's relatively straightforward, which is that prior work have come up with a metric for how effective a tail is. And it's basically how much body rotation do you get for some unit of tail rotation. So if you know that your tail can move 180 degrees, you can compute how much your body moves. And the more your body moves for that fixed sweep, the more effective the tail is. In the case of the inertial tails that I was talking about, that you're just sort of swinging this mass, you can actually compute that as just a function of your inertia. It doesn't matter sort of what motor you're using or how you get there, as long as your angular momentum is conserved, which it usually is for these sort of falling animal problems, then it's just a straight mapping from your inertia as to how much it moves. And so you can use that to basically show that the more inertia your tail has, the better. There's been a little bit of work on aerodynamic tails. This was featuring some work out of a lab in Berkeley, where they were looking at sort of these more centimeter or millimeter scale systems with more of like a sail kind of tail, but they weren't really actuating the tail. It was basically just a rudder that they were using. And then one of our collaborators in this project, and Patel, the one who's doing the Cheetah stuff, had some models showing that the effect of fur, where they like measured they put some tails into a wind tunnel and got some drag coefficients, put that into a model for angular impulse and found that they got about a 20 or 30% increase in angular impulse when the Cheetah was running quickly to the turning. And so that's inspired us to say, well, okay, if the Cheetah looks like it can do this, we think we can make a tail that has more drag than a Cheetah does. But how much can we actually push the envelope? And so then we started looking at a model for, okay, how does drag actually affect how well a tail moves? That starts with a pretty well-known equation for quadratic drag, where the force that we get out of a body moving through a fluid is a product of a couple different things. Density of the fluid, we don't really have any control over. We got a drag coefficient in there, this cross-sectional area, and then the velocity of that body squared. And so what we can do is say, okay, for a given sort of tail, we are really more interested not in the force at some cross-section, but the applied torque that that drag would produce from a certain tail. And so you can integrate that across the course of the tail, and you get this nice equation at the end here for how much torque you get. And the interesting thing here is we still get these same sort of terms, but we get this length to the 4th term, which anytime you see scaling like that is sort of an interesting sign that the longer a tail is, the tail should be much, much more effective. I'll talk a little bit more about scaling when we get to how we actually design the tail. But just because we have this model, it says, okay, we can predict how this effective this thing is going to be in terms of how much torque it can apply, but is that enough to actually do something useful? We had this nice metric for inertial tails, which said, okay, it's just however much the body moves or how much the tail moves. Unfortunately, because now we have sort of nonlinear physics, our momentum isn't conserved. We can't compute this in closed form like we could before. But we can still sort of approximate that same number by just simulating that model, measuring how much the tail moved relative, or how much the body moved relative to how much the tail moved for a particular behavior. And then that's our stand-in for this effectiveness metric. So still measuring the same thing, it's just we can't compute it as a function of inertias anymore. And so then we can compare that, that number that we get if we turn drag on or off. So basically if we're testing in a vacuum for the same tail or not. And by comparing those two effectiveness metrics, we can subtract that out and see how much the aerodynamics actually come into play. And so we did that for a couple lengths of tails. I'll break this down. So for each of these plots, they're showing for different body length tails. So that the longer your tail, as I mentioned earlier, the more effective you get. So the y-axis here is that measurement of effectiveness. So higher curves mean better tail. And the x-axis here is a metric of inertia. So basically, as x increases, the tail gets heavier and heavier compared to the body. And this sort of bluish curve, diagonal curve, is if you don't have any drag, it's pretty straightforward. As you increase your inertia, you increase your effectiveness linearly. But we see that this black curve, which is when we add in the aerodynamics, is for long tails much higher than we got with just the inertial ones. And interestingly, has these sort of local maximum. Whereas before with an inertial tail, it's relatively straightforward. If you want a more effective tail, make it heavier or make it longer. For the aerodynamic tail, if you sort of have two choices, you could try to make it pretty heavy and then adding mass is helpful. But if it's light enough and you have enough drag, adding mass actually makes it worse, which is sort of counterintuitive. But essentially, as you're sort of at very low masses, any sort of incremental mass is going to reduce the effect of the aerodynamics and sort of this like quadratic rate, as opposed to the linear rate that you get from increasing the inertia. And so you sort of have two design areas where if you're going to have it be light, you really want it to be as light as possible. But that's actually kind of nice for robots that we don't want to add a bunch of payload. We can also see that, especially for longer tails, very light tails give us about the same amount of effectiveness as very heavy tails. I see something in the chat, but I don't know if I can pull it up. Let's see. There we go. Terry's asking about perhaps a deployable and retractable drag chute type design. Yeah, I'm going to talk about that, especially when we get to some of the limitations of the kinematics. Okay, so this model looks good. It's got some interesting results, and it shows us that we do think that we can probably make a tail that uses these aerodynamic effects to do something interesting. The tail that we ended up making was, this is about as light as we can get it, but I'll talk about that design. So I mentioned that we had this model, and now next up, it's time to actually build the tail. But we can use this to sort of guide how we're going to select the materials, the dimensions, the shape, all sorts of things. And in particular, we're going to try to take note of the scale. So this length to the fourth term is interesting. We basically want the tail to be as long as we can. So obviously, as you get longer and longer, the design gets more cumbersome. But there were some tails that we found in nature that were about twice as long as the body length. So we went with that. I'll get into that a bit more. But we see that we scale quadratically in angular velocity, which is interesting. So we want to be able to rotate the tail pretty quickly. And if we're moving fast, then we might be able to get even more benefit. It's linear in the drag coefficient, so not as good as Cordic, but certainly we want to have as high drag as possible. And interestingly enough, is independent of inertia. So again, that's nice for us. We can make it as light as we possibly can. So what we're shooting for is a long, lightweight tail with as much drag as possible. So we went about trying to figure out how to do this. We have first started with looking at different types of fur in different craft stores and modeling them a bit. We had this sort of elaborate test setup where we could drive the tail around. This is okay, there we go. We could sort of drive it. This is in slow motion and measure the torque that the motor was outputting and get a metric for how much the drag coefficient was. But pretty quickly we realized that we don't really, since we're just trying to be inspired by nature, we're not trying to mimic it. We can do a lot better than just fur. And so pretty quickly we went to plastic. And then it took us a couple of iterations to sort of reduce the scaffolding weight, just because just getting the material for this tail to not collapse on itself was tricky. That was where a parachute design, we were sort of inspired by a parachute design, but the tricky part is getting it to be sort of uniformly shaped, because at low speeds, if you're just moving this sort of parachute-like material, if it hasn't been sort of filled with air yet, you get basically no control authority. So we did want to add a little bit of structure to the system so that even at low speeds, it would still have this large cross-sectional area that we needed. We also, in looking at sort of this, the shape of the tail, thought about maybe if we could add sort of like a wiffle ball type effect, if you can add holes in the right space. So one of our master students did some fluid simulations of airflow through various shapes. And so we got some nice images from it, but in the end, it found that this sort of just regular half cylinder tail was by far the most effective and had the highest drag coefficient. I think someone sent something in the chat and I'm clicking the button, but I can't see it. So if someone wants to ask me a pressing question, go for it.
I was wondering if for keeping the material of the tail expanded, if magnetic repulsion in the material would help you to do that and it would be more controllable. than just a static framework, so to speak. If you could actually increase or decrease the magnetic polarity in a material that would cause it to puff out or shrink depending on the magnetic polarity of fibers or discs in the material.
Yeah, I think fibers, certainly. The tricky thing is keeping the mass down for sure. So it would have to be one of those materials, and this is where my material science knowledge isn't so good. But I do know there are some of those sort of shape memory kind of materials that can have this sort of variable stiffness. If you apply some current to it, it becomes more stiff. Those types of things would probably would be perfect for something like this.
Yeah. When you talk about rotation too, I just want to make sure I'm understanding this. When you talk about tail rotation, you're talking about the tail rotating from the origin point, kind of like a fan in a fan blade motion, 360 degrees, not a spinning motion around the central core of the length of the tail. That's not natural, but I'm just trying to make sure I understand the mechanics of what you experimented with.
Here, so here's like the cross section of our model.
Yeah.
So the sail here in this image is we would rotate this clockwise about this axis. So this is the motor in the plane. So the sail.
It's moving in a cone type shape, not in a cylinder type motion, right?
Cone. So in this case, it is moving in the plane. So it's basically rotating.
Well, I'm trying to think of the right way to describe this. It's not rotating around the long L axis, so it's rotating off that pivot point,
yes.
Right?
Yep.
Okay.
Yeah, so this is like a pin joint here.
Yeah.
Coming out of the screen.
Okay.
There'll be videos later on that'll show, but yeah, that's correct.
Okay.
Interestingly enough, there has been studies into conical motion, because if you do conical motion, then you don't have this limited range of motion issue. You can kind of keep spinning and you can get torques in like different directions. So people have looked at that, and there's sort of interesting things you can do. The issue is it becomes less effective because your moment of inertia goes down. Okay, so we tried a couple different designs and then decided that simple is the best. And so we ended up, I guess I could have gone forward to this one. So we ended up with this sail tail, basically at the end of this long thing. So the half cylinder shape was, and both from the tests that we ran and then looking at sort of measured numbers in the literature, this was basically the best you can do for this sort of planar shape. Interestingly enough, not that many resources on maximizing drag. Seems like everyone wants to minimize it, but there's not as many applications where you're trying to get as much drag as possible outside of like parachutes. We knew that we wanted it to be as long as possible. So as I mentioned, we sort of went off of the largest tail to body ratio that we found in biology, and then similarly scaled for the width of the tail. And we pretty quickly realized that because it scales with length to the fourth, really most of the contribution is coming from the sail closer to the end of the tail. And so we could have this sort of half cylinder shape run along the entire length, but it's really not getting much more benefit from all the stuff down here. So we can save a little bit on mass and also maintain the rigidity of the structure, because if we had this entire system, the entire length of this, then it gets very flimsy because we're trying to use very lightweight materials. So in particular, we went with a 1 centimeter diameter carbon fiber shaft, which makes up the center here, and then 1/4 millimeter polyethylene film. This entire tail weighs about 100 grams, a little over 100 grams, and the robot weighs 7 kilograms. So we're quite a bit less than the weight of the robot. Also, in case people are curious, we basically just use one of the leg motors for the system. So it's a brushless motor. We added in a gearbox to get a little bit more torque because we did some optimizations and we didn't need the speed that these direct drive German motors needed. And that it gave us a bit more increase in power, or not power, but in effectiveness. And then again, this is a Minotaur quadrupedal robot that we're using as sort of our base platform. Okay, so we've got a tail. We think that it's effective, but now we've got to sort of put it to the test. And so we designed 2 tests. One of them was sort of inspired by what other people had done for the inertial tails, which is basically similar to where the robot walked off the cliff. The robot is sort of strung up on its end and has to reorient by 90 degrees within one body length. as sort of a basic test of how is this an effective thing? Can you do the time constants of the tail work out that you could probably stabilize large disturbances? So that's what the test looked like that we were sort of benchmarking against with an inertial tail. Yeah, they have it walk away at the end to show that it didn't break any legs, because if you do this without the tail, it snaps the legs. And then we also wanted to check beyond just sort of falling in the air, can we actually use this tail, because it's lightweight, we're not adding that much mass to the system, to perhaps enhance some of the base locomotion of the platform. And so again, inspired by these cheetahs, we wanted to see if we could use the tail to perhaps increase the acceleration of the system by actuating it while we're sort of running forward from rest into a run. So I'll talk first about the aerial self-righting one. A quick note here that I'm sure you all know that every hardware experiment always goes flawlessly.
Yeah.
Not at all true. We ran into issues with the, this is one of the master students on the project, Cameron. When you're working with lightweight tails, the issue is that they can sort of break easily. So especially when you smack them into your environment. So safety harnesses are usually a good thing. This was before we actually added the gearbox, and we thought that we needed 2 body lengths to fall. And it turns out that sometimes if you fall too far, your legs might be screwed even if you land on them properly. So things weren't looking great at this point, but then we did some more optimizations and found that, oh, if we add this gearbox to the motor, we can get it to be much more effective. So we added the gearbox, and then the first test, it was too much torque for our 3D printed bracket from the motor to the tail, and it immediately snapped on. So after a few tries, finally, then we can get this nice behavior where we can see the tail in action, rotating, and we land nicely on 2 feet. Actually, go a little too far. And then we can stand up and walk away. And so on the right here is measured for motion capture. The dotted line is the prediction from simulation with sort of a roughly measured drag coefficient. And then we get our response in red. It hits the ground here. So data's kind of junk after that. But the interesting thing is we can simulate this without any drag. So just 110 gram or whatever tail. And we get about almost 2.5 times greater rotation when we include the drag versus when we don't. So we can confirm that we're getting significant amounts of contribution from the aerodynamics from the sail. We also then tested it for linear acceleration. So we ran a trajectory optimization to try to compute what's the maximum acceleration behavior that the robot can get, and then applied it to the motor with the tail deactivated and then with the tail removed. So you can see an example of that behavior in slow motion here. We push the tail backwards as we jump forward. And on the right, we can see that if we look at our velocity over time, so acceleration is sort of these average accelerations are shown in the dashed lines here, that when we have the tail activated, we can access these sort of faster velocities sooner in the behavior when we have the tail, compared to either gray, which is when we don't have a tail, or blue, which is when we have the tail, but it's just turned on. And the interesting thing here is, so we can accelerate 18% faster than if we don't have the tail, showing a pretty good contribution from actually using it. But we also accelerate, I think it was about 12% faster than when we don't have a tail at all, which by Newton's second law is kind of interesting. We've added mass to the system. You would think acceleration would go down for the same force. But because we're using this extra mass in sort of an intelligent way, and by doing external work on the system, we can increase the acceleration of the overall platform, which is interesting. So we demonstrated that these aerodynamic effects actually can be useful for a wide variety of legged robot behaviors. It also comes with a couple other advantages. So because it's lightweight, as I mentioned, the payload is much less. It's easier to sort of just strap to your robot. The nice thing is that it doesn't have this momentum transfer issue. So because it's so lightweight, we get a lot of sort of effective inertia from the drag. The drag is pushing back on the tail, and it feels heavier when we're sort of moving it. But then when you want to stop the tail, drag is now helping you decelerate it. And so you don't, because you've done external work on the system, you don't have to sort of dump a bunch of energy back. So you get these nice sort of effects, control authority in one direction if you want it, but you don't have to sort of pay the price. And because it's so lightweight, you can kind of do whatever you want with it, and you're not going to be using a bunch of torque to sort of hold it wherever you want. So you get because you can perform external work on the environment, it helps with this momentum transfer thing. It also helps in the case that once your tail stops rotating, if you're falling at least, the body will actually keep rotating because you've done external work. Whereas if you don't have these aerodynamics, as soon as you stop moving your tail because angular momentum is conserved, then the robot stops moving as well. So it can continue to be effective. The downsides, as I sort of alluded to, is because length is so important to the effectiveness of the tail. If you have limitations on the workspace of the robot for whatever the application is, obviously you might not want a twice body length stick sticking out the end of your robot. I think there are interesting ways to solve that, and I'll talk about that in a little bit, but that's sort of the main downside is we're no longer constrained by adding mass to the system, but we are still adding sort of size to the system. As a side note, this effectiveness metric is behavior specific. So we had to sort of simulate a behavior to get a measure of this metric. And so the behavior we simulated was this self-righting one, which is why we see it acts pretty similar to the model. But in the forward acceleration case, because it's not quite as well suited to the advantages of the robot, we don't see quite the same benefits. So I think there is work to be explored by applying this to other behaviors besides just accelerating or recovering from a fall. So to summarize, this drag that we've measured and sort of quantified certainly does seem to be able to enable these behaviors and to a pretty large degree, especially when we can engineer the system to be that way, with the nice added benefit that we've reduced the mass quite a bit, which is one of the sort of main Achilles heels of these tailed systems. And that allows us to sort of rethink how these tails that typically only go on robots for sort of research to sort of showcase that they can be useful. We can start to think about applying them in sort of new ways and new systems that now that we don't have to pay this big sort of mass budget. But there's still a lot to learn from biology, which is that even these tails don't really look like the one that we made. For one, they don't have a big sail on the end, but they're also relatively compliant. And so I think that's a nice property that when the robot, or when the animal doesn't need the tail to do anything, it can sort of either like tuck it in or fold it up. Or if it smacks into the ground, it sort of, it just passively complies to the ground and it doesn't sort of mess with the robot. Whereas if we smacked our tail into the robot, because we have this sort of rigid rod in the middle, it could either break the tail or mess up what the robot is doing.
It seems like
yeah, go ahead.
Sorry, it seems like it would be interesting to experiment with, and you may have done this with a retractable tail that can change its length and also rigidity by, again, electropolarizing it or something else so that you can, when you're not using it, it's relaxed. So it's less, it's got less, what do you call it? Static torque on the system.
Yeah.
When you're not using it, that's a negative component. Like this guy sitting on the branch, his tail's acting as a counterweight right now, but it's probably nearly completely relaxed.
Right.
What is that animal too, by the way, in the middle?
This is I think it's called a giant Indian squirrel. This one. Yeah, so it's a cheetah, Indian squirrel, and then this is a jerboa.
Yeah.
The interesting thing about these ones, especially the jerboas, you notice that their tails are actually pretty skinny, except for at the end they have this little tuft.
Yeah.
Which I think sort of, I can't say that it was evolution sort of led to that because of the model, but our model certainly indicates that more effectiveness at the end of the tail is better for aerodynamics. Yeah. So it's interesting to sort of see that analog.
Yeah. Or it could be just for attracting a mate. It just looks sexier.
That is the tricky thing about tails, is that we can never really say that this tail it's never really meant for stabilizing the system. It's meant for all sorts of biological things, but a lot of animals seem to have them and use them for interesting things.
Yeah.
I think another solution, and this is where I'll talk more about what I'm working on now. We'll see if I get around to sort of novel designs. But I think probably the start is you could just add sort of a passive hinge or clutch or something at the middle of the tail. Just have like two rigid sections, and then it could fold up on itself. So you wouldn't have to have sort of an entirely compliant structure, but you could still sort of, if you don't need the tail, you sort of fold it up and then it's not sort of sticking out so much.
I saw some links when I just looked up animatronic tail to research being done to add a segmented tail to humans to give you more capability.
I've seen that one. Oh, it has a name. I don't remember what it was called, but
Yeah,
that one is.
it's using a different animal. They're modeling it after a different animal, like a vertebrate. But
It's got like multiple segments. So they're trying to approximate a continuum tail like this, but they're doing it with sort of discrete number of links.
Yeah.
I like that idea. They always looked extremely bulky to me.
Oh yes, yeah.
Certainly, as an advocate for tails that should be lightweight, because most people don't want to, especially with Lego robots, every bit of mass matters, because that's mass that you're not adding to your motors,
Right.
or increasing your payload capacity. So I'm a little cynical of the application of that, although the idea is very cool.
So some of what I looked like in the research was they being done for space research where your mass is not a problem because you're floating in weightlessness.
Yes.
And I thought that was kind of an interesting application. It seems like your tail research here, in one sense, could be applied to the landing of space probes and making sure that they're righted in the position you want them to land in if they're not ones that can bounce and do a full 360 and not be damaged.
Right.
It seems like it would be interesting to be able to control a landing probe, or a bit anyway, manipulate it with that.
Yeah, that's a good point. For a landing probe, then perhaps you could. People have studied, there's a new professor at CMU, Zach Manchester, who has a bunch of work on using tails to control satellites. Because, I mean, if you're in space, aerodynamics don't really exist. So obviously you can't use that. But the nice thing about those systems is that the time constants are so slow, you don't really care so much about, can you move enough in time? You're more interested in, can I move in the directions that I want? And so there's a lot of cool research about with a 2 degree of freedom tail. So I've showed a 1 degree of freedom tail. It's only got one motor.
Right.
With a 2 degree of freedom tail, you can rotate it in those sort of like conical motions to get rotation about the 3rd axis. It's sort of like the parallel parking non-holonomic constraint problem, where you can't parallel park, you can't move a car straight sideways, but if you can sort of turn the wheel and press your pedals the right way, you can get the net effect of moving into this area. With a 2 degree freedom tail, if you sort of move it the right way, you can move in any direction given enough time. Which is something that's plenty of.
Although that problem has been overcome by the one automotive manufacturer that has Mecanum wheels on their car where you can go sideways.
Yeah, exactly. If you can break non-holonomic constraints, problem certainly gets easier. But yeah. So okay, this is a good segue into the last few slides, which is that the control that we've applied here is sort of for these example behaviors. But when Lego robots are walking, there's all sorts of different disturbances they might see. Angular momentum is definitely not conserved if you keep smacking your legs into the ground. And so this is a little video that the college put together. They wanted me to write a controller, and so I just wrote some like basic angular velocity based controller. It's basically just flailing the tail around. The tail's not actually doing anything intelligent to stabilize the body. So I'm working with a master student right now on how we can add more intelligent control for the tail that sort of has an idea. Either it can also choose what the legs do, or it has an idea of what the legs are doing and how that affects the system, so that you can more intelligently stabilize when you're walking over a curb, for example. So this was sort of a proof of concept for the design, but the control certainly still has a lot of room for development. And that sort of leads me into, I have a couple of last slides on some of the other things I'm doing in the lab, and then I'm happy to sort of keep talking about whatever. But most of what I've been thinking in the last year or two is how we can better control and plan for the system so we don't have to be trying to recover from these failures in the first place. So here's the same video that I showed earlier of this robot trying to go over this log. Right now, it's just got I'm just sitting behind the camera, controlling it with a joystick and telling it when it should jump. But we would like to automate this process. The robot it'd be great if the robot could see that there's this log in front of it and either reason about, oh, I can't make it over this log, I should walk around it, or you know, I think I can jump over this log, I can use that behavior that I know, and not have to sort of succumb to these disturbances in the first place. And so the work I've been doing with them since then has been developing algorithms to do this motion planning. And I could talk a lot more about that. It's complicated because we know a good amount about the math about how these systems move, which is usually what you need in order to sort of plan what they should do. But because the algorithms have to compute so quickly in real time, it's really hard to do that with the full model. And so there's a big challenge in how do you represent your system in sort of a reduced order model way, where we're getting at sort of what parts of the system we think actually matter, but still in a way that allows the robot to sort of move effectively. So here's a visualization from this planner that I wrote. So on the left here is sort of our separation of how we want to solve this planning problem. At the top is what we're calling the global planner, which is basically, think of like Google Maps, but for a legged robot, that says, okay, I should walk over here if I want to go from the start to the goal. And if there's a big sort of gap in the middle, then I should use this jump primitive to be able to jump over that. And so given a map of what the terrain around it is, it can use this and then inform the controllers so that we can tell the legs what to do, to follow the footsteps, those types of things, to do this more intelligent planning. So I can definitely talk more about this, but that's what I'm working on a little bit more recently. A couple other things that our lab is working on that you all might be interested in. We've been working on something that we call a mini Rex. So in some of those videos that we saw before, there was that 6-legged sort of cockroach-inspired robot. We've developed and released open source a mini version of that you can sort of make yourself with off-the-shelf parts. There's some 3D printed and laser cut parts for about $200. And it's actually pretty robust at if you're looking for sort of a cheap, small, education outreach focused walking robot. It's a great platform for that. We used to do outreach events where we would show up with our Minotaur robot, but we only had one. And with a classroom of like 20 kids, it was hard to sort of get their hands on the system, especially for a legged robot. But we can make, you know, we have 5 or 6 of these in the lab now, and so everyone can have, you can have one robot to 4 people, and then the controls are super easy. There's just like a couple parameters that you can tune and see how that affects the gait. And as you can see, it can get over some pretty interesting stuff. So we've been working on that, and the motors that we're using some Dynamixel motors, which since have been upgraded in what I've heard to be a lot of interesting ways, and are also cheaper. So we're looking for some people. We're working on updating the model. We'll probably release that at some point, and we think it might even be able to actually like run. These motors right now aren't fast or strong enough to be able to run, but that should be coming soon. I've also been working on not just legged robots, but robots for doing specific tasks. So we've been looking at automating the soil sampling process if you're trying to do like an environmental study. So here's a robot we call Patrick in our lab. It's a tracked robot. I definitely wanted to feature this because the base platform here is from Rover Robotics, and I saw from your upcoming presentation that Nick from Rover Robotics, I think, is talking to this group in October. So we've loved it, and he should have some interesting things to say because he's definitely thought a lot about robots and different interesting applications for them. This one's got a rototiller on the back, which looks pretty gnarly. It's our closest robot to a BattleBot for sure.
That's pretty cool.
Oh, and lastly, I want to throw in, because it's Juneteenth today. I felt like our lab has been thinking about this quite a bit. We've been working a lot with this relatively new organization called Black Robotics, which has been developed in the last year or so. They've been supporting Black scholars, especially in robotics, offering different sort of community outreach things, advocacy, methods of accountability for different systems. And I know they do a lot of work with either different sort of local organizations or ally networks. And so they're sort of a good resource to think about sort of diversifying and bringing more roboticists to the table. They've also got, we've worked with them to develop this reading list of a couple different prominent Black roboticists and some of the works they've been doing. And there's some interesting things there. So I do some links in here on the slides as well as some other similar organizations in similar fields, sort of grow the network.
Cool.
Yeah, so thanks for listening to me talk for a bit. I should point out that Professor Johnson is my advisor, and Amir Patel were the ones that sort of headlined the tail studies. So they've done a bunch of cool stuff, especially Amir, who is a professor at the University of Cape Town in South Africa. And I also threw some links in here to the papers for both the tail stuff and then the more recent work that I've been doing on the planning stuff, if you're interested for more.
Very cool.
Yeah, happy to take any questions.
Is it advantageous or sorry, in your research, was it advantageous at all to look at the dynamic effects of things like bullwhips and such in terms of what they can do? Because it seems like there's a lot of dynamic power that you can get from being able to express a tail in a whip-like action. And I'm not sure, you may have mentioned it. If I missed it, I apologize, but I didn't quite see anything that alluded to that.
No, I haven't thought about that. My initial thought is I'm not sure that how much of that power would get translated to torque about the base. And I don't think from any of the tail biological systems that I've seen, I don't recall seeing that sort of motion. But I have to look at the math more. I don't think I've actually looked at a mathematical model that could predict that. I'm sure it exists. I just haven't.
Yeah.
But yeah, I'd be curious if it had an effect on the base.
I would think it would be applied more to animals like monkeys that have articulated tails that actually use the tails to grip branches and other things like that. The lemurs, use their tails in navigation, but not as much in gripping. I think, if I remember correctly. So that, yeah, that's where my mind was kind of headed is, yeah, it is just those types of applications.
We did look a little bit about one of the main reasons that in our plot of the when the robot was falling and we measured it with motion capture and compared it to the model, we had some sort of lag behind the actual system, and we think that's mostly due to the compliance, because that carbon fiber rod, when we add 14 Newton meters of torque, it deflects quite a bit, and we were wondering if we could use that. Looking at the model, it seems like it would probably just add a delay between the motor actuation and then the actual force that you get. So that I don't know if you could harness in sort of a useful way, but that's totally different from this sort of whip-like motion. So I'm not sure about that. That'd be interesting to look at.
Yeah. And in practical applications, and I know you mentioned part of this, I didn't catch all of it, was where do you think the direction of the research will take you? Or do you have some targets on what you really want to apply this to? Like I was mentioning, the lunar, Mars lander or something like that.
Yeah, I think so. We are going in a couple directions. Most of what I'm doing is thinking more about the planning controls, because I think there's a lot more sort of unknown there. But I am working with someone on the adding the control that includes what the legs are doing. And so I see that as sort of the main direction. The aerodynamic part is just making it sort of more practical. If you can get the system, because I think as is, it's still not quite practical enough to put on the robot just because you want it there, and not because you're doing research on it.
Yeah.
If you could get it to that point, like biological systems seem to have, then I think its application is really anytime you're deploying a legged robot in these unstructured environments, whatever the applications for that are, an extra system that you can add to make sure that you're not going to be falling over, or even if you do fall over, you can use your tail to help you.
Right. I was thinking with the whip application and an extensible cord, so to speak, as opposed to a rigid rod, if your robot encounters something that it cannot climb over because it's too tall, or it starts falling, it could direct out the whip to capture something like a monkey's tail and keep itself from completing the fall, or redirecting its motion so that the amount of force in the fall would be lessened by significantly. Literally sort of using the whip like a third arm to reach out or to go over objects. So it would need to be something that, in my mind, is controllable at the end, so it can wrap around something and hold. But it seems like there's a lot of ways that could be done, with having it be almost like an extensible electrical cord with magnetic fittings or something at the end of it that could be polarized and cause it to spiral or circle something. That would add a lot of capability to your robot, with getting out over objects that might be significantly larger than itself.
Yeah, certainly there's a lot of sort of extra degrees of freedom we didn't explore with the design. Like, we just have a basic carbon fiber rod. I mean, we know we want to keep it light, but like you said, playing with sort of directional or variable stiffness should allow for a lot more things. There was in 2018, there was an RSS workshop on exactly, it was like multimodal appendages or something. It was basically a workshop where a bunch of people were like, what else can we use tails for? There was some interesting insights. There might be videos of that online somewhere. I'm not sure. But.
Okay. Cool.
I'd be worried about the shock loading. If you're falling and you grab something, especially if you're a rock climber, try grabbing something as you fall. Essentially what you're doing is you're going to stop at a short space, and that's going to put a huge amount of energy into that system. And the way climbing ropes deal with it is that, number one, they're rated for a certain number of falls, and secondly, they actually are somewhat stretchy. So if you're going to rely on a system to catch yourself, the shock loading could just rip that appendage right off. So something to keep in mind if you're designing a system like that.
Yeah, I think that should be, you could still, that's an axial load, and I don't think we really subject the tail to axial loads that often. So you can certainly probably have a design that sort of is compliant in that axial direction, but in these tangential directions where we're using the force, then it's relatively stiff. But yeah, there's a lot of, if you can sort of pick and choose those directions at any time, that would be ideal for sure.
Yeah, I like that. Good point.
I've also got some, if we wanted to talk about the system that we're actually putting together on a quadruped, and I heard some people talk about Ross, so I threw our little flow chart of our communication network, if we wanted to talk about those. But I'm mostly mechanical engineer by trade, so you all probably will dwarf me in your electrical knowledge. But we've got a lot of information that we're passing along. Whenever you now need to reason about what's in the world around you, things get way more complicated in terms of what sensors you need and what things you need to try to measure.
Yeah. No, thank you for including that, though.
Oh, there's a video here too. This is the current status as of like a week ago, of visualizing our current walking controller, planning footsteps, and then getting a nice. I'll put in a plug, since we sometimes put in plugs for tools. It seems like, I don't know if people have used Plot Juggler within a ROS framework, but if you need to live plot multiple signals, would recommend it very highly.
What's it called again?
Plot Juggler.
Oh,
I don't know what people were throwing around ROS, so I don't know if people have used RQT plot as like the regular plotter. That's terrible. This is much better. It's basically written by, I think, one person, but it's sort of the right kind of person where they've made it their brainchild and added a lot of functionality. There's some memes that show up on the splash screen when you first load it, so it looks really unprofessional when you first open it, but after that, it's great.
Thanks for the warning.
Do you know Red Whitaker?
I not personally. I do know the name. He's certainly a legend at the Robotics Institute, and one of my co-PhD students, I think, has him on her thesis committee, but I haven't interacted with him personally. He does mostly field robot stuff, right?
Well, I remember him from DARPA Grand Challenge and reading about that in Popular Science magazine and other various articles on the web and wherever else. So
Yeah, he's still around for sure.
good, cool.
Okay, do we have any more questions? Should we wrap up? Okay, sounds like no more questions. Just a note, folks, we'll stop the recording here in just a moment, but if anybody wants to hang around, feel free. The meeting itself, I believe, will stay open, just like before. So yeah, we'll go from there. And thank you very much for the presentation, Joe. It was great.
Yeah,
Yes,
thanks for having
thank you
me.
very much.
Learned a ton.
Yes.
Glad to hear it.
Okay, thanks, folks. See ya.
Yep. See ya. I have to run so I can get ready for my camping trip.